Chain rule, also known as a function of a function, which is what in engineering we used to know it as, and it's gradually sort of changed into the chain rule. But if you look at this, can you all identify that that does equal that?
Oh, yes.
Because you've got du and du there, they'll cancel out, won't they? And you'll be back to this. So that little neat little trick, and this is the kind of thing you do in maths, find little neat tricks to solve problems you can't solve. And the neat little trick gets you there. Okay? Everything you do in maths is based on that actually. Right from the beginning. Okay, so the best way to do it is to show you an example. So this is when, hence the name function of a function, it's when you've got a function you have to do before you can do another function. So a simple one would be, for example, now I've been telling you, I'm going to go with t. Now you know the solution to this one because it's in your table of derivatives, but it actually comes from, because it's a known result, it goes in your table of derivatives, but it comes from this method that we're going to do now. So what you've got there is a function, you've got to take t, times it by 3 before you do the sine function on it. So it's a function within a function. So that's why we used to call it a function of a function. A chain rule as well, because it's chain, you do one bit and then you do the next bit of the chain. So it fits as well. But I think the chain name comes from that, stretching out, because you can do it, keep doing, multiplying it out like that. Okay, right, let's have a look. So what we've got to do is a little workaround. We can't do it, so what we say is, we say let's do a substitution. So this really should be called substitution. Let u equal 3t. So we've made a decision, we're going to say that u equals 3t. We can do this, and this is quite normal when you get long formulas, isn't it? They say, right, we'll treat this bit as x bar, for example, in standard deviation, and it's actually finding the mean, but they just put x bar. And it's the same kind of thing, it's making a longer bit, you know, putting some smaller bits in to make it easier to read. So it's normal practice, but we're going to use it in our case to solve the problem. So we say let u equal 3t. So that means we've now got this. Would you agree? Would you agree with that? That's correct. Now our formula there says dy du, and it says du dx. So we can do, we're following our formula, we can do a dy du on this. I'm going to change, bear with me, just to make it easier with that notation there, I'm going to change this to a t, to an x. Apologies for the mess in your notes. It works the same, but the formula is using x, so I want to leave it the same. Okay. So sine u, I can do a derivative of that, and that would be dy du, because the second term is our variable is u now, not u, but u. So that would give me dy du is going to equal, what's sine u, derivative of that?
Cos.
So Ahmad?
Sine u, that'd be cos minus cos.
No, it's sine, so it's going to be...
Sine
Cos.
No, just cos.
No.
Oh, just cos, and then
Making it harder.
Yeah, you
than
need
you
the bracket at the edge in it.
Okay. Next one is this one. I'll do it here. Du dx. So that's that one, part of the formula. So you've got u equals 3x, so it's du, that's the dependent variable over the rise over the run over the independent variable. So we're going to get, what's 3x? Derivative of 3x? 3, yeah. It amuses me because these are the easy ones and these are the ones you always get stuck on. If they'd been squared on the x, you all would have got it straight away. No squared then, it takes a second. Okay, 3. Right, that's all well and good, but my formula says that I'm aiming for, I need to bring them together in a multiplier. They multiply each other. So in that case, dy dx is that formula. So it's this cos u times this. Okay? See what I've done? You see how mathematicians work these things out, these little ways to help them get there. Very clever. Right, there's one problem with that though. It's not a solution, is it? Because it's a u, and u actually doesn't have any.
We don't do use.
We don't do u's. No, you're right. It's not related to what we're doing. But what does u equal?
3x. U equals 3x.
Yeah. So I'll put that back in. So I've now got this.
3x.
And I'll bring the 3 to the front.
Yeah, make it.
Because that's the normal. Right, does that look?
That'd be 9 cos.
What have I done? I've taken. You know this from your table of derivatives. The answer to that is 3 cos 3x. And what did I get? 3 cos 3x. So that's where your table of derivatives from. If you do a few examples with different numbers, different scenarios, you see it always works out the same in your cosine and sine derivatives. So that's why that enters into your table of derivatives as an example of one you can always use. A shortcut function. Okay, you don't have to do that every time.
Makes life easier.
It makes life easier, yeah. Which, as I always say, we like, don't we? Engineers, we like to make life easier. Okay? Right, another example. So you see, not that hard in the end, is it, when you get down to it?
All you're doing is inserting, isn't it?
Yeah. Yeah, basically what we're doing is manipulating things to make it work for us. But as long as you follow all the rules of maths, you're okay. Nobody can insult you for it. You can't arrest you for it.
Yeah.
Okay.
Yeah.
Right. Another one. So this is a bit I can pause the video. I can cut it out so I can do a little dance. I'll put this will be one of my videos and my outtakes.
Yeah, do
You know, that'll be the one that gets all the results.
bloopers.
Yeah, my bloopers. Or not, yeah, bloopers when the bloopers and not bloopers when I'm just prattling about, yeah. Was it you guys the other day I went, don't do it? Was that with you?
It's not worth it.
Right, another example. If I can put my serious face on again. Right.
It's recorded.
Yeah. Yeah. It's all live. Forever. It'll be all over the internet.
Hopefully one day, then. We get cut out.
So let's have a look at another one. Another one that, right, I told you this earlier. I made a statement. I said that if you did the log of 2x, I said this one wasn't in your table of derivatives, and I told you, if you remember, I said that the answer would be this.
1 over x.
1 over x. But I said it was actually log of 2 over 2x. Don't ask me I've written log there. But that's your solution.
Did you have to connect up?
Huh?
The LN.
No. I try to write it in a way where it's obvious that it's log of n, but it's natural logs. But my handwriting just isn't that neat. isn't that skilled. So that obviously equals the same as it. So let's see what happens from this principle. So we've got a function inside a function. You have to do the 2 times the x and then log it. So if you're doing it in your calculator, you do that. Your calculator would do that function first and then do that if you were using it as a function. Find the gradient, we've got another problem. So it's the same again. What am I going to let u equal? This is about as hard as it gets.
Here, yeah.
Everything inside in a function. So 2x. Figuring out what to do let your u in equals probably possibly the hardest bit of this, I think. Most likely where you could go wrong. Okay, so now I'm going to apply my formula. So now y equals log of u. And you know the derivative of this, like log of x, which is a u. dy du, let's use my variable, 1 over u. Okay. Another bit, du dx. What's 2x, derivative of 2x?
2 over 2x.
2 again.
Just two. Or just two.
Just two, yeah. So I'll put them back together and I'm going to get this. So dy dx is going to be then brought back together, which is going to be
2, 1 over x. 2.
over u.
Oh.
And u equals what?
X.
2x.
2x. So they cancel to 1 over x. So there you go, there's the proof. That's what we call a proof. So you use your table of derivatives and take the shortcut, though that one's not in your table, is it? The one with the number in front. But if you want to test it with 2 billion, if you want, you'll get the same result. Out of interest, let's see what happens if... Am I okay to rub this out?
Yeah,
I've got this.
Yeah.
Let's just do a little tweak. Let's say it's 2x squared. And then when you do your derivative of 2x squared, it'll be easier than doing your derivative of 2x. Because you seem to get that quicker. Right. Okay, let's have a look. So what's u going to equal? Yep. 2x squared. Total 2. So again, let's not jump the gun. Y equals log of u still. And we know that answer from last time. 1 over u. Derivative of this one. So du dx 4x, yeah. The 2 disappears instead of 1 now. Bring them back together. So 1 over u times 4x, or bring them together like this, 4x over u. Substituting for u, so don't forget that stage, 4x over that. Okay. So interesting result. Different things have happened, haven't they? Yeah. If you keep trying different ways, you start to spot patterns. Sometimes though, you just get too many patterns to remember. That's why you get long table of derivatives. You get it more with integration actually, the integrals, the solutions. But yeah, there's a pattern develops, and you do start to spot that pattern. But basically, what's happened was the derivative of what's inside has gone to the top. I'll have to do a few to test it, but I think that's always the case. Okay? Alright with that? Could have been worse. Could have been worse being taught. Right, let's do another one. I'm trying to think a nice one. What we like for time? Got 10 minutes to the early finish. Either way. I'll have to edit this out of the video once. Class does not finish early, I'm only kidding. It goes right to the end. Okay, let's have a look at another one. Let's say 2 plus x, yeah? So not easily done from your table of derivatives. What is u going to equal?
2 plus x.
Yep. Hassan, what's u going to equal?
2 plus x.
Thank you for coming. Yeah. 2 plus x. Okay? Probably want it in brackets if it ends up multiplying anything. Let's have a look. So again, again jumping the gun. Y now equals e to the u. What's the derivative of e to the u?
E to the U. E to the U.
E to the u, yeah. It's the one, it's the easiest one. E to the x or e to the u or e to the t. So dy du is just eu. Okay?
You.
You. Yes. Now, du dx. What's the derivative of this? What's the derivative of 2? Of 2? Nothing, yeah?
Just
Derivative of
nothing.
x.
Just X.
It's nothing.
Just nothing.
What's the derivative of x?
X.
1.
1.
Yeah,
It's always the easy ones that catch people up,
Yeah,
catch people out. So that's that. So bring them back together.
1 over.
So what we got? We've got this times 1. So it stays the same, that bit.
Yeah.
Substitute back in for u. I'll do it on the same line. U equals that lot.
Just anything.
Nothing happened, did it?
The same.
Yeah.
All that for nothing.
All that for nothing. Curious, curious. Right, let's now try it, and then this will just take us up the whole time nicely. Let's do, children, you know the answer to that one. Let's prove it very quickly. Very quickly. What's u equal?
2x.
Okay. That means that y now equals e to the u.
Yeah.
So dy du equals what?
EU.
Is that right, Hassan?
Is that right?
Do you agree with anything you tell him?
Yeah.
Derivative of du dx equals
2x.
2.
Alright. Oh yeah, 2.
Yeah? Bring them back together as per a formula. EU times 2. What have we got? 2.
Now wouldn't it be 2 EU?
Yeah.
2 EU.
If you want, yeah. It means the same.
Alright, what is in the U2?
Right, well, yeah, well, substitute back in for you. We've got. So there's your proof of that other one that's in your table of derivatives. Interesting that you got a total different answer to when it was something plus the x, that just stayed the same. So when you multiply the x, you get the. What I didn't tell you before, I might have told you before actually, yes I think I did, that when you find the derivative of e to the x is always the same, so that means that you get that the answer to the function, the solution to the function is the same as the gradient. So that's what's quite unique about it. Okay. Okay, I think that's a good point. Let's stop with that.